Good morning, everyone. My name is Ash Blue. I'm here this morning speaking on A-star pathfinding for JavaScript and beyond. I will be primarily focusing on the A-star algorithm implementation and exactly how you can use that in your various projects to create interactive pathfinding. My name is Ash Blue. A little bit about me. I currently work at Clever Crow Games, which is my own game company, currently building a RPG in HTML5 so we can distribute it to multiple platforms, PC, Mac, Linux, game consoles. Currently, that's what we're focusing on. I'm actually also one of 4 authors who worked on HTML5 in Action, which is by Manning Publications. I wrote the sections on interactive APIs in HTML5, which is Canvas, SVG, and WebGL. And also, too, I worked on various other blog articles, a company called The Nerdery, Wikia, if you've heard of them, all working on interactive solutions with JavaScript. So let's start by establishing exactly what we're going to cover for pathfinding. As far as pathfinding goes, we're primarily talking about having 2 different points, being our blue dot and our red dot, and being able to traverse from one point to the other through obstacles. Now, in your pathfinding implementation, you're probably going to have more than just the 2 squares here, probably multiple things you have to work through. You want your code to be able to figure out how to get through as many obstacles as you can throw at it without having to go through and write a bunch of wonky code to try to figure that out. Also, too, the AI pathfinding algorithms that we're going to be talking about are not just solely focused on games, which is, I think, what a lot of people think of when they hear A-star pathfinding or AI, the most practical applications. Actually, every time you load up Google Maps, that's all pathfinding data from the server coming back to you that you can actually get that will tell you how to get from one location to another. Pathfinding can also help you with acquiring resources. So, for example, like ship routes, trucks, different things, getting different areas. It all helps with optimizing that and figuring out the most optimal routes. Also, to weather patterns, I know we'll actually use different forms of AI and pathfinding to try to figure out where storm fronts and things will come in. One of my favorites, the most recent, is robotics engineering with computer vision. There are various Arduino libraries out there that you can pick up that you can use to actually traverse with the A-star pathfinding algorithm we're going through. You can technically go through the data, hand it back to you from computer vision library of some sorts, and then actually make a robot move from one location to another. A little bit more complicated than that, but that's a general idea. Before we start talking about A-star, I want to talk about a couple of other pathfinding options and why we're specifically not using them. The most common one, majority of you probably here have done, if you've ever tried to move anything from one point to another around anything whatsoever, you've probably used a brute force method. Majority of people have used this, and it'll get you a little bit of the way usually, but usually you end up creating a bunch of matrices, a bunch of arrays and data, and you try to move around it, traverse it, and it works to some degree. You've probably seen implementations of this yourself when you've been playing a video game and all of a sudden the AI like cracked out and walked into a wall and just stands there and stares at it. Or even an algorithm where you're trying to traverse data and go through something and it just stops. A lot of times it's because someone's using brute force and they didn't really write into their algorithm a way for something to get around obstacles in certain situations. If you don't write your algorithms correctly, you will run into all kinds of like little caveats and things where you hit up against a wall or something randomly stops. Another popular algorithm I've seen a lot of people use, particularly at the meetup I run out here in San Francisco, which is the HTML5 Game Developers Meetup. I've seen a good number of people try to implement Monte Carlo algorithms for pathfinding. I think the reason why that is in a lot of computer science courses, they teach you Monte Carlo algorithm. They usually actually don't teach you a lot of other potential pathfinding algorithms, things that could be used for that. So people pretty much go through and end up doing a flood fill to try to look for various locations for their path to traverse. And while that may seem like a good alternative if you don't know A-star, the performance results in JavaScript can be very lackluster. I had a guy that I met a few months ago who was using flood fills and Monte Carlo to try to calculate items moving on pretty much almost like a small tic-tac-toe board. And it was actually stuttering because the iPad doesn't have acceleration on the JavaScript algorithms that it's interpreting. Like everything's a lot slower on an iPad and whatnot, so you would actually notice the speed drop-offs because he was using this flood fill algorithm essentially. and A star would have fixed that if you had used that. So another good reason why I should be using A star. Jasheka, which is one of the last algorithms, which is pretty much A star is a derivative of that. Jasheka pretty much means you go through and you check absolutely everything on the board. So every single tile or every single pixel on the board, you would look at that and figure out if whatever object it is you want to move can move there. And you have to examine every single pixel, every single item. A star doesn't do that. A star just only looks at the most pretty much direct route possible and automatically takes it. It's pretty amazing. They call it the golden solution, actually. Reason being is it's very, very customizable. There are algorithms that are faster than A star, but the problem with them is there's just such a massive code base. As you see here, we're going to walk through the implementation of A star from literally beginning to end. It's only going to be like, I think, it's just a little bit over 200 lines of code, I think, roughly. Like a lot of these more advanced, more optimized solutions, we're talking about thousands of lines of code versus a few hundred. And if you've ever worked on large code bases, that always quickly becomes a nightmare. A star is insanely fast. It'll literally take pretty much the most direct route possible right off the back. It'll try to traverse a little bit out of the way of the most direct route possible a few times, but you don't notice that or see it. It usually doesn't affect performance in most cases. It's extremely reusable. The A star implementation that we're going to be looking at here, I've actually used it on several projects now. I pretty much just copy and paste the code and just pop it in, and it literally just magically works. And I can go in a few different places and edit some of the code, and it'll just magically work. And I can customize it to include things such as gravity or birth of width for the pathfinding algorithm to go through things, because normally A star by default is just a straight line drawn to try to get to the most direct path. Okay, so let's take a look at here. We have a little map, and we want to get our hero to the treasure. We have a character named Cole, which my wife picked this up for me from the game that we're working on. Just some quick little prototype graphics. But this guy will walk literally the fastest path possible to the treasure chest. And this is a live implementation. So as we click, it'll actually traverse the data. And he just magically knows how to get there, which is pretty cool. So let's figure out what in the world is going on right now. So first thing that you need to do with A star is you need to take a map and you have to break it into the term they usually use, voxels, which is a really fancy pants word for pretty much squares. So you break everything down into a grid, and you pretty much go through and label all the boxes, which we'll look at in a second. Jumping ahead, sorry. It's earlier for me still. You don't want to do individual pixels, which is a common mistake a lot of people try to do with A star off the back. If you do individual pixels, you would have to then traverse every single pixel as a voxel. And as you can imagine, it only takes me 1, 2, 3, 4, 5, 6, 7, about 8 steps to get to the path I want to go. If you did individual pixels, that would be hundreds to get there. So the smaller the pixel size you go, the more of a performance degradation you're going to get. The next thing you need to do is you need to identify the tile types. Right now we have the gray looking tiles are all blocked, which means our character cannot go there. Anything that doesn't have anything on it, we're just automatically marking with the number of 1, which will be the step cost. Step cost being how much does it cost to actually step on this individual voxel. Then after that, you'll notice that I've marked a 2 for water. So one of the cool things about A star is you can label different step costs for different kind of tiles, or create special tile types such as like sand, water, traps, whatever you want. You can technically put that in the map, which is pretty cool. And it really doesn't care as to exactly what the data that you put in there represents. It just takes a step cost. Also, too, we need to mark every time an A star. We have to have a start and an endpoint. Otherwise, it'll just crap out and return us nothing. And the next thing we need to do then is the A star algorithm. As you'll see here, I'm going to run through this. It'll actually go through and examine one tile at a time. As you can see here, it starts with the first tile, pumps out surrounding tiles around it. And what it's doing right there is it's looking at the first tile, starting out, and it's looking at possible paths it can take, and it's giving them a step cost. So it's going to take the next, whatever it assumes is the next best tile, and also, once again, it's going to get the surrounding nearby tiles and increment the step cost. And it's going to keep doing that until it gets all the way through and it finds literally the shortest path possible. And it tries a few different ways, particularly because of the fact that we have different blockers in places and we also have some water tiles which are a little bit more expensive. So hence why, if you didn't notice it, tried to walk over the top a little bit more. So one of the ways that I was able to figure out what was the best possible next step to take to try to advance the pathfinding algorithm is it uses what they call a distance heuristic. Pretty much the distance heuristic is a fancy word for a really simple equation that tries to figure out the distance from a tile to the endpoint. There's two different ways that you can go about implementing this. There's Euclidean and there's Manhattan. Pretty much Euclidean has a square root in it, and it's more of a diagonal calculation. So Euclidean is actually much more accurate than Manhattan, but because of that square root, causes a really serious performance degradation in JavaScript. So pretty much in every single game algorithm, you're going to see Manhattan being used. I don't think I've actually ever seen anything use Euclidean in the pathfinding algorithm, but it is there and it is good to know about. I think Euclidean is more of the kind of a classroom book answer, and Manhattan is kind of the thing that you kind of use a bit more in real life, I guess. So let's take a look at the heuristic in action and the actual values that this pathfinding algorithm is pumping out for the heuristic. So it's each of these individual points that it's giving us evaluates each tile. It's actually pumping out a number, which is what it thinks is the distance from that tile to our red square, which is the endpoint. So as you can see here, as it gets closer and closer, it's it gets closer and closer, and it's always going to prioritize the tile with the lowest value. So you'll see here, because it's 5 over there, it's going to check that one, but it gets higher, so it backs off. Then it goes to the 4 over here. And then it's going to add the tiles. And then it's going to move on there. So like I said, always, it's kind of hard to see some of the values up with the graphics. They overlapped a little bit. But yeah, that's how it was able to get through all of that data. Oh, and by the way, too, I know some of this is probably a little bit fast, and it's a lot to take in to figure out A star at one time. But these slides are all up for you, so you can sit down and go through these of the walkthroughs and everything. I'll give you the link for that at the end of this year. So now we need to talk about open and closed sets. So the way that A star is actually able to evaluate if what tiles it should look at and what tiles it shouldn't, it actually dumps them into pretty much a gigantic stack of tiles. So our open set is ones that haven't been evaluated yet. The closed tiles are already evaluated tiles. And we'll look at here a live walkthrough now of kind of putting everything together of what it looks like when you take all of the open set, the closed set, the step cost, and the heuristic. Putting all those together, we get A star. So it starts out there adding the first tile, adds it to the closed set since we're evaluating the steps around it. And as you can see here, just let you know the 10 up the top here of the one in the far left corner. The 10 represents the total cost of the algorithm, which is the first number down there on the left is the step cost. The 9 is then the heuristic number. So giving us a total of 10. So then it's going to evaluate the lowest one, which of course is number 8. We're going to add number 8 to the closed set, look at its neighbors. So then here it's going to take whichever one it feels like, which is going to be the top one because they both are the number 8. So it's going to prioritize that. We have number 8 again. But it will take the lower step costs over a lower heuristic cost, which is important to know. So that's the reason why it prioritized 2 over 3 to take the next step. So it'll look at those. It's then going to take 8 back up there because technically it's closer. It'll evaluate 10, which is a really high number, so it's going to back off on that. Then you can see here it's adding some more around the 8, which is the lowest one. It's going to take the lowest cost. Can't see on here, but the value I think jumps up to 7 or something like that. It's a bit of a higher number because of the extra cost of the water tiles. So it's going to try to evaluate those. Avoids the water since it knows that it shouldn't go through the water again because it's a higher step cost. Once again, back to that. We pretty much have a direct path that'll figure out from there, taking the steps. So you can see there, actually, if you look through all the data from the beginning of Cole, where he started out our little hero to get him to the treasure, it pretty much follows 1, 2, 3, 4, 5, 6, 7, 8, 9, water tile being 2. And then it's actually able to go through all that data and traverse back through in reverse and give us an actual clear path to get through this. So pretty cool. We didn't actually have to evaluate the entire map. It just got literally a direct path. Very powerful, and we'll take a look at exactly what code it takes to implement in your projects. So the first thing we need to do before we actually look at what we're going to call the Pathfinder, we have to create a map data, some map data or a map model. You need to abstract your map data away from the Pathfinder separately. It's a separation of concerns, among other things. And a lot of A-star customization will happen in the map itself, not in the actual Pathfinder. There's only one particular area in the Pathfinder that usually ever gets customized. The map itself, you can just go crazy and edit however you want to integrate whatever data that you need. We will be using John Riesig's simple JavaScript inheritance for instances. Pretty much it allows JavaScript to very simply mimic classes since it's a prototypical language and really doesn't support that naturally. And a few of the methods we'll talk about here is we have a setMap method that we'll talk about, which pretty much sets our map data and exactly how we do that. We need to do out-of-bounds checks too, which is to make sure that when we're traversing through the grid data, we don't get an out-of-error index from the array. And also we'll take a look at get neighbors, which is actually how when you evaluate a tile to figure out who the neighbors are, you can figure out exactly what data should be returned. So setMap, which is the first method we're looking at, breaks the map down into literal voxels. So as you can see there, taking that map with everything in there and converting it to zeros, ones, and twos in our step values. You'll want to use a multi-dimensional array, usually 2D. You can also use a 3D array for this. I have implemented this exact A-star algorithm with a 3D for a turn-based strategy game. It was actually really, really easy. All I had to do was pretty much go through and change setMap and get neighbors. So it will work with 3D with just very minimal extra coding. If you're using jQuery, a cool thing is if you've got everything set up in a table or a bunch of divs, you can actually just loop through all the data and create your grid that way, which is kind of nice if you're using DOM. Also, complex games will require several different maps. Collision, entities, maybe if you have some other changing data. And you can actually layer this map data into your map API. We won't be going into that, but it is something that is totally possible to do. Done it before on projects. Sometimes if you have a massive amount of data to traverse through and look through, what people will do is they'll only evaluate what they call grids on their map. So they'll actually cut their map grid up into several smaller sections. Games such as Call of Duty and like StarCraft actually all use this with their pathfinding solutions. They just cut the map up into little tiles and evaluate all of it. So you can do this with massive things like Google Maps, I'm sure does that also. Our out-of-bounds checks, really, really simple. Like I said, just make sure that we're not violating the length of our open and closed tile sets, the map data, so we don't get an out-of-bounds error check. Get neighbors. This is where majority of the customization that you're going to find in maps takes place. So when you've got your map set up, you can actually then say, hey, I want to get the neighbors to this individual tile. This is where you can go, well, I want to return 3D data. So you can put a z-axis in here, and instead of returning like these 4 corners, which just gets the currently evaluated tile and sends top, bottom, left, right, you could do above and below. You can also add in diagonal tiles. And this is all you have to do to get the algorithm completely working with these things. 3D, there's a few more notches, but like I said, for diagonal tiles, you just return the corners and you're done. It's pretty amazing that that's all you have to do. The completed map data is just literally pretty much what we talked about, other than a few helper methods, such as like get cost. which just gets the map cost for interacting with it. It's very, very simple, very, very small amount of code. So let's talk about the Pathfinder API. This is where our instance or class that's going to go through and actually traverse that map data, turn it into something we can actually use. So each creature in your game or whatever you're doing, like let's say you have like a car and you have, or I'm sorry, several cars on a map, every one of those cars is going to need to have a Pathfinder. You don't want to try to mix and run pathfinding algorithms off of the same Pathfinder. Long story short, it will be disastrous. You'll start getting multiple paths returned. I've tried it before. You don't want to try it. So when our Pathfinder is complete, it will actually return a full path that we can navigate. A few of the topics that we'll overview here, looking at the Pathfinder, is working with the closed stack and exactly how we're going to interact with that. Open commands, working with the open stack, which is our open array. We're going to also take a look at a find path walkthrough, which is literally what finds the path, and which is the kind of core meat and potatoes of this API. And then assembly last, of course. So let's talk about closed commands. So we're just going to add in two simple methods here, add closed and enclosed. Add closed, just literally you handed a tile, pop in the closed tile into the closed set, you're done. Then for checking if something's in the existing closed tile and getting it back, we just pass in the step data and we just return back the step item if it's found. If not, we just return false. Very simple for interacting with the closed API. Then for the open commands, we have add open, which does the same thing as close. We have remove, which we'll go through actually and strip out the item that we currently have from the open stack. An int open check just to see if it's in there. And here's the important one that's a little different from closed, is you want to get the best possible open in our stack. So when we loop through that open data, we need to go through, find whichever one has the absolute lowest cost possible and send that back immediately. You can tweak get best open a little bit if you wanted to be a little bit more specific about additional metadata that you might want to use to prioritize different tiles. You could do that if you wanted, but it's rare that you would need something like that. So then here's the core meat and potatoes I was talking about, which is the find path walkthrough. This is where I might lose you guys a little bit. It's a little bit complicated, but I'll try my best. So as we start out with our current tile when we first call the method. And then we go through and we're going to have neighbors. Neighbor record. A neighbor record is the only one that'll probably sound a little funny in here of this list of variables. A neighbor record is just looking to see if there's an already existing record in the closed tile set to make sure we don't double evaluate things. And if we do actually do a double evaluation, that we update the reevaluated tile to a new value. The reason for this is because if you're going from, say, like two different directions that you're evaluating, and let's say that they both collide, they could actually cause the algorithm to technically stop evaluating altogether and crash on itself. So this will prevent that from happening. A lot of people will forego the neighbor record check, which I did when I first implemented it. I was like, oh, that code looks complicated. I don't know what it's doing. I'm not going to integrate it. And then I started getting like all these times when I call the method and it would return me absolutely nothing for a path when there was an obvious path to get somewhere. So we start out by adding our starting step after we've reset the app, which is pretty much all reset is doing is just resetting the closed and open stack. We add in our open tile. We then start a while loop, which is going to infinitely run until it's complete. While loop will increment a step, take a look at the best possible open that we can get. We'll then check immediately to see if a goal has been discovered, because we don't want to go any further than that if a goal is available for us. And if so, we'll return that with build path, which we'll look at next in a minute here. We'll then move the current tile that we have from open into closed, because we are currently evaluating a tile, and we're looking at its neighbors, so it's no longer valid. It's currently evaluated. We then take all the neighbors for the tiles, and we look around them, and we evaluate each individual one by getting the step cost, calculating the heuristic, seeing with the neighbor record if it's already available, and then based upon that data, we either add a new record or update it. So, and then we go through, repeat that process, continuing to look at all the neighbor records that were placed into open tile set. So once we have all that data, what the hell do we do with it? Well, we assemble a path. So recursively, we're going to build through, and we're going to pass in a single tile. So one important thing that you can actually see here, I have little models on the back end that just represent each of the tiles. You record the parent of every single tile when you go through the neighbor. So if you call a neighbor, you would say, hey, these tiles that we're all neighboring were a parent of this. And that's actually how you recursively traverse back through. So you go from the end, once you've discovered the goal, and you move back through all those parents. You dump them in a stack and send them back, and then you have a traversable path from the pathfinding data. So not too complicated. If you're used to recursive path building, it's pretty much all it's to it. That pretty much sums up the gist, before we move on here, of A-star pathfinding and how it works. Do you guys have any questions? I know some of this is probably like, what the hell did I just look at? I have no clue what's going on right now. It is a lot to take in. Oh yeah.
So you said it's a modified Dexter, and in Dexter they use the heap to produce find the minimum. So in new code I've seen that you can loop in through all the neighbors to find the minimum.
So yeah, what it does is it has an array that it dumps all the closed tiles, which are the ones that have been evaluated, and then it has the open tiles, which are the unevaluated tiles. So what it does is it goes through as an open tile, then closes it to evaluate it, gets the neighbors, which are the surrounding tiles, and then takes each of those and then puts them in closed as it evaluates them. That way it prioritizes which one gets evaluated.
I guess you always have a step when you evaluate the shortest path. Right? Out of all the pathways, you need to pick the shortest one.
Yeah, no, well, it's that's the crazy thing about the algorithm, which is really awesome, is that it always will figure out what is the absolute shortest path because it uses the heuristic to figure out which tile it should evaluate next. And then it also takes into account the step cost. So those two things together, it literally just magically finds the fastest path possible. There are some like weird cavets with it that you can get into where it'll not quite find the fastest. It will always find the fastest path, but maybe not the fastest path that you want sometimes. So like the way that this is implemented right now too, like if you had water, you may like normally you would have walked through water, but if it's a shorter route, it'll just go straight to the water. So that could be something that you might not want for an AI. So hopefully that answers it. I'm not too sure if that answers the question. Oh yeah, I mean, I can talk to you after.
How large of a map can you do this with until it
Infinite.
That's what we need to fit the memory.
Yeah, well, you can infinite. The map can be of infinite size, because with A-star, what you do is you start breaking everything down into grids once you get large enough. So you would say like maximum tile evaluation size of say like 100 by 100 grid of voxels, and then you would combine those grids together if they overlapped. I don't know if you played a lot of real-time strategy games, like Call of Duty or StarCraft, which I know is a really popular one. They actually pretty much use A-star on what they do to evaluate different areas at different times. They actually take the data, break it up into smaller grids, and evaluate each of those smaller grids one at a time, so that way they're not evaluating everything going on. So, but like I said, you can technically, in theory, it's infinite. So
how does JavaScript compare with the other languages in terms of
well, I mean, A-star is what I would recommend for any pathfinding with JavaScript because of performance reasons. The other, like Jajeka, which is what I think a lot of people end up relying on. It's a lot easier to understand. There's a lot more information out there on it. Just evaluates every single tile and then sends back the best path. That was a little bit more accurate sometimes, but at the same time, we didn't even evaluate, we maybe evaluate half the map.
No, I mean like using Python or some other like more traditional language. Why should I use JavaScript?
mean, like, technically you could use any language you wanted, but, like, the thing is, like, for JavaScript, there isn't a whole lot of information on doing A star with it. And so there's, like, all the implementations I looked at were pseudocode or C++. I mean, you could use Python or anything else. I mean,
there's pros and cons.
Yeah. It's just a tool that can be used in any language, really. So, I mean, there's really no difference in
But
implementation.
if you write in browser games, right, that would be like just run in browser.
Well, I know some people, too, if you have a more complex algorithm that's really heavy, you may just have to evaluate everything server side and send it over.
Right.
So if you've got something super heavy, but like I said, like A star should technically be able to evaluate everything because you can do it on the front end just by breaking things down into grids if your file size is too large. Yes?
Just a question. Have you considered like genetic algorithms, for example, for bigger problems? But you just said that for JavaScript, then it's like it's not efficient at all. But have you played with it, like genetic algorithms to solve these kinds of problems?
Bigger algorithm?
No, the bigger problems.
Well, I'm currently using a tweaked implementation of this to like evaluate real time in a game with dynamic potential collisions, which creates a lot of issues, like 100 by 100 voxel tiles, and it's been running really, really well. I mean, like I said, like it's all a matter of implementation, and they're really like you won't find anything better algorithm-wise, literally, to run.
But I think for bigger problems, genetic algorithms are better for Pathfinder because they're made for very huge problems, like very complicated problems. And it's better to use a genetic algorithm because you can let it run for like days. Just give it the problem, let it run for days.
Well, we're talking about
maybe
JavaScript.
it's not efficient here.
Oh yeah, well I mean we're talking about JavaScript, so I mean no one's gonna really necessarily leave the browser on for days to run something. But yeah, I mean like this is a tool for a specific problem. I mean there are always better tools out there for different things. So like I think what algorithm, like you said, people would run for days would usually probably be a check algorithm that would go through and check literally everything and every possible outcome. So I would steer away from Checker though in JavaScript. It runs slow on mobile devices. On the desktop, it's fine. Any questions? Or?
Do you think there's any libraries out there for JavaScript specifically which you think implement this spot on?
Yes, I actually have a couple recommendations. I have still a couple other slides on base usage of A star. Does anyone know what time it is?
9:42.
9:42. Okay, awesome. Still got some time then. And last question?
Oh yeah, so this will like find the path and then move the actor, whatever it is.
Yeah, you can do whatever you want with data to get it. So.
Is there any way to like prioritize, like if there's multiple goals, to prioritize goals inside the algorithm, or like how would you go about, like say I want a little, guard to just walk back and forth until the hero comes into view or something like that, and you have to like run the Pathfinder every time between the two possible goals, or like how
Yeah,
do you
you'd probably have to.
solve
I would say you'd probably have to run it between. I mean, the cost of that is, I would assume, not too expensive to run between the two possible goals, and probably when you return the data, you could probably return some extra metadata with it because when you loop back through everything, you could you could evaluate various costs and additional params. Perhaps if you had some extra values that you didn't want to get evaluated, that would like or this quest is like a priority over this quest if they're the same distance. So, or if you had a quest that was more important, you could actually tack on an additional tile value starting out. So you could say like, hey, if like saving the princess, is more important than slaying the dragon, you could give starting out an extra 10 or increment to the tile costs, and then that would help to evaluate that. So it's pretty flexible. Sometimes you have to think outside the box a little bit to get it to do specific things, but that's a good question. Let's talk about pathfinding with gravity. I actually wrote a library called Pathfinding Platformer. I'm still working on it a little bit, but it has pretty much everything you need to start doing A-star pathfinding with actual platforms. Let me see if I can load it up here. So when you click here, find a gravity-based path, it'll actually find from the green to the red dot actually how to get from one path to another. Let's see here. It actually goes through and adds a slew of other data on the back end with this algorithm to try to figure out exactly where it can and cannot jump. If you ever do have to do anything with gravity and A-star pathfinding, I highly recommend looking at this. There's pretty much no information out there on how to do it. The only information you'll find is forum boards of people pretty much crying that they can't figure out how to get a gravity-based pathfinding solution. The one tip I can give you if you have to do it, though, is that it's pretty much figuring out where you can't go. So it's like figuring out where ledges drop off. As you can see here in this implementation of the game, not for the Workman Dragon, we actually have the gravity-based pathfinding solution, and it just pretty much looks at exactly where it can go. Oh, yeah.
What about when things are moving or the tiles change from time to time? Is there...
That's when you want to have multiple maps, actually. So you would have a collision map, and then you'd have a regular map, and you'd have to constantly, the game itself would have to update that collision map, or an additional collision layer. So you would probably have all your static objects, and then you'd have a dynamic collision layer on top of that. So you'd have to look at multiple maps in order to evaluate. That's a really good question, and that's something when I first looked at this algorithm, I'm like, how does that work? So another thing that's really, really great to know about is clearance values. Like, for example, if we wanted to drive a tank through a really, really tight passage, we could do that with A-star. We have to sit down and look at clearance values. I don't have time to really go into this and exactly how clearance values work. Pretty much what it does, well, actually, it's not too hard to explain. You can see where this one starts here. What it does is it pretty much draws a box, and then pretty much looks at each neighbor, and then increments the value going up to figure out exactly what the clearance is. Really, really great article by AI game devs. I recommend here the tutorial link. We'll explain a ton of stuff on exactly how to implement this, and the coolest part about it is if you need support for it in A-star, I think it's 3 lines of code if I remember correctly. And that's all you have to add, and then everything that you literally evaluate in the game will then have clearance-based pathfinding. Someone I remember earlier was asking about box JavaScript solutions for pathfinding. So here's the catch: is majority of them out there are like weekend hacked projects or something someone's thrown together and they're not maintaining. Most of the ones I've looked through were a complete and total mess on the back end. We looked at how many lines of code for implementation. I think it was around 200 lines total for a reusable system. Most of the systems I looked at were like thousands of lines of code, so no one knows what's going on there. It's a total mess. These are a little messy for the most of it. Like Easy Star is actually the most simple one I've seen. Easy Star, just literally pop it open, send in your basic pathfinding data, and it just magically works out of the box. Really great, but very, very basic. Pathfinding.js actually has some interesting implementations of various pathfinding solutions, not just A-star. It'll do like jump checking and some other things. Pathfinding.js is hard to customize if you need to. If you need to have a very specific solution, like you were saying, like with dynamic collision data, or you need to break your grid up into microgrids to evaluate information faster, you should really implement it from scratch, just 200 lines of code. It'll totally be worth your time versus trying to hack apart someone else's code that might not do exactly what you want. For more learning resources, I recommend Introduction to A-star and A-star for Any Language, which is a Wikipedia article with a bunch of pseudocode on exactly how you can pretty much implement A-star abstractly. Any additional questions, remaining time that we've got?